Okay, today we'll start with certain circuits, arithmetic circuits. So we'll today concentrate on adders. Although we did a few of them, a few of the basic adders we did in our VLSI design course, we'll see some advanced circuits in this course. Okay. So let's first quickly revise what we did in the last VLSI class, and then we'll build further on more complex circuits in this class. Okay. This was the 28 transistor adder. Now this is the truth table which is given out here, right? So if you see here the carry out here, so the carry is more important because that needs to be propagated from one stage to other, right? Whereas sum is generated locally for each bit. So our target will be to first generate the carry out here. So there are, if you see here, there are 4 conditions at which the carry is generated. One is an ABC, so that is actually redundant. Other is an A and B both are high. This is A and C are high, and here B and C are high. So this is the equation for the carry. So straight away we can map it like this. If you take from here, if you take C common, then it will become a B or A and then and C. So and then you have an dual of that PMOS on top of it. So you generate carry, and then you this is, since you are you are not assuming that the complementary signals are available out here. So what we are making an pull down network from these signals directly, and then we are using an inverter to invert that and get the carry out here, right? Now that carry, now we write an expression for the sum. Now instead of again implementing this whole expression, if you have a look at the truth table out here, if you see here, this is 0, this is 1 0 1 1 0 0 1 1 0 1 0. So other than for the top 2 conditions, okay, other than for the top 2 conditions, it is invert of carry, okay. So I can write, so there is one sum here where all 3 of them are 1. So I write ABC here for this one, okay, and then invert of carry, I write invert of carry, but it should not get inverted for this particular condition, okay. And what is this condition? When all of them are 0, okay. That means, now if all of them are 0, that means if other way around, I can write A or B or C. So here if any one of them is 1, this will be 1 here, okay. In that case it will not be carry bar, but this will be a 1, okay. And since this is 1, so this condition will be taken care of by this particular expression. Now I use carry, and then along with this carry, A or B or C, okay, in the pull down network, and then I have this ABC also in the pull down network, and then I have a sum bar inverter, okay. So this was the 28 CMOS adder, and then we saw that okay, here we had a drawback. This is 1 2 3 4 transistors which is stacked up. Here also there are 1 2 3 4 5 6 7 8, so many transistors are stacked one above the other. So we thought of making a mirror adder, right? So in the mirror adder, okay, for the pull down network it is the same. For a pull up network, we grouped the zeros instead of grouping the ones, okay. So for the pull up network, this is what A dash, this is B dash C dash, if you group this. Similarly, if you group this, it will be this is 0, and this is A dash B dash, and similarly this corner one and this corner one, if you do it, it will be C dash and A dash. Again you take C dash common, you will get the same expression similar to this. Only thing is there is an inversion there, and this inversion can be implemented by using an PMOS. So we implemented this particular circuit. So you are all very familiar with this circuit. This was the 28 T transistor mirror adder which was implemented. Here if you see here, the carry delay is 2, okay, because if you consider this as a single gate, okay, so this is one inverter delay or one gate delay, and then you are using one more inverter to generate carry, okay. This is carry bar, and then you use one more inverter to generate carry. So the carry delay is 2. whereas the sum delay is 3 because you are using carry bar as an input. So carry bar needs to be generated first, then sum bar will be generated, and then sum. So the sum gate delay is 3 out here. Okay, so this has got is this okay till here with all of you? All of you remember these things from your VLSI days, right? Is it okay? Yeah, let me open up the chat. Okay.
Yes, sir.
Yeah. Okay. Now see the full adder, we implemented it this way with gates. Okay, right? We can also implement it using mux. Okay. Now when you are implementing it with mux, okay, it is like A XOR B, and again one more XOR. So within 2 gate delays I get the sum out here, right? This is, so this XOR also, if you see the CMOS implementation, XOR can be implemented with single gate delay, delay of an inverter. So this is actually sum will be 2 gate delays, right? And then what about carry? So suppose this XOR is 1, okay, so you are giving selecting S, so you have this carry in being propagated towards the outs, right? If I take this, if XOR is 1, okay, so this will be given 1 here, so this carry in will get propagated 1, right? Now if XOR is 0, so there are 2 conditions, right? One is 0 0, one is 0 0, right? If it is 0 0, then there cannot be carry, right, in any case, right? So XOR is if it is 0 0, AB is 0, then I have 0 here, A is 0, so that will get 0 will come out as an carry. But there is another condition for XOR to be 0, that is 1 1, right? For 1 1 also this will be 0, so this is 0 input to the mux. This is the controlling mux, right? So in that case also A will be this 0 will be transmitted here, and since A is 1, it will be 1. So 1 1 also has to generate a carry 1. So this will work perfectly like an full adder. Now if you see the delays out here, okay, so 1 gate delay here and 1 gate delay here, right? This mux is also 1 gate delay approximately. It will be lesser than that if you implement it actually, but worst case scenario. So you have the sum as 2 gate delays and carry also 2 gate delays when we are implementing using mux. Is this operation clear to all of you? Is the mux based full operation clear to all of you? Yeah. Okay, I have not enabled the mic for everybody. No, I have enabled it. Okay, so if I get some responses in between, and it will be good. Okay, so this is mux based and full adder. Okay, now XOR gate. Now we talked about this XOR gate, right? So let's see how an XOR gate. Now if you see XOR gate, this is the truth table, right? So I have an 0 0, okay, for which it has to be output has to be 0. So if you see here for 0 0, this will be off, both of them will be off, but this will be 1, this will be 1. So this Y will be pulled to 0, right? And here I have an this one, okay, for 0 0, this will ensure that this VDD is not connected, and this one will ensure that this VDD is not connected. So this condition is met out here. So similarly, if I go to now next condition 0 1, right? 0 1 means this is off, okay, because one of them is off. This is also off, right? But here what happens? Here I have B A bar and A B bar. So for these two conditions, okay, these two branches in the bottom will be off. One of these branches will be on. So this will be charged to 1. So I have a 1 here. And now for the last condition for 1 1, okay, for 1 1 again this will be switched on and it will be pulled to 0. And since I have a bar here in both the branches, this the top PMOS will be switched off. So this is how an XOR gate. So now if you see XOR gate is also 1 gate delay. So here it is XOR, so we are talking about 1 gate delay only. So wherever we see XOR gates, we will talk about we will consider XOR as a single gate delays. Okay. Similarly, XNOR. Okay, XNOR is although we are not going to use this further in our particular topic, but I thought, okay, let me put this, because in case you have to implement XNOR, the only change which you need to require is swap the inputs, right? A bar B bar, so you just put A bar B and A B bar, okay, and here AB is there in the bottom, here you put AB, and here A bar B bar, this A bar B bar goes on top, and B bar and this B A bar comes in the bottom. So if you swap these inputs in the same structure, you will get it as XNOR. So you can write a truth table and verify that functionality also. Okay. So this is how, and with CMOS we implement XOR and XNOR. Excuse me. Right. So this is again the same circuit. It is just since if you assume that only signals are available and their complementary is not available, then you need to generate, okay, these two. Now the only problem with that CMOS XOR is now 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, 12 transistors will be required. Okay, and then so that is the one issue. So let's see if we can have a better option. And also if you assume that this input complementary is not available, then one additional gate delay because of this inverter also will be introduced. Okay, so we don't want those kind of things. So for our adders and all, we know XOR is very important function for an adder. Like it comes for sum, propagation. We learnt about how to generate sum and propagation, right, in our previous class, in VLSI class. So XOR is a very important gate. So let's see how to implement an XOR with an transmission gate. Okay, so now this, if you see here, this is using only 6 number of transistors. So there are several conditions. Let's assume A is equal to 0. Now when A is equal to 0, okay, this transistor will be switched on, right, and I will have 1 here. So this transistor also will be switched on. So what is Y now here? Y is just B, correct? So whatever is B, and since this is a complementary PMOS and NMOS, so you will get full rail to rail voltage out here. So this takes care of the two conditions, right? Now similarly, if A is 1, then I have to get a B bar at the output. So now if A is 1, obviously this transmission gate gets switched off. So if A is 1, I have a VDD being given here. I have VDD being given here, and this ground, because A is 1, this will become 0, 0. So now this inverter is powered, and I have B bar coming to Y. So right, so XOR is what? If A is equal to 0, right, if A is equal to 0, Y is equal to B, and if A is 1, then Y is equal to B bar. So that can be implemented by this circuit. Okay, so this particular circuit, it saves a lot of area also, right? Now if you consider that these pass transistors generally they don't have that kind of delays, so this also can be considered as an single gate delay. Okay, so all you can say it's an one inverter delay and one pass transistor delay. Okay, you can call it that way, but otherwise because there is one inverter here and then one pass transistor here, but pass transistors have negligible delay, so you could just call it as one gate delay for this particular circuit. So this is how a transmission gate based XOR can be implemented. Yeah, is this operation clear to all of you? Yeah, okay. Excuse me. Okay, now how this can be used to make an full adder. This is an XOR, right? AB XOR, it will come here. If it is 1, it will be here, and this is one inverter, so this inverter will come here. So whenever AB XOR is driving this transmission gate, okay, so whenever propagation is, ABA XOR is what? Propagation, right? That is, one of them is 1, If one of them is 1, if carry is 1, then the carry gets propagated. Is it okay with all of you? Right? What is carry? Carry is generate or propagation into a C in. Okay? Propagation is A XOR B. Right? That means if propagation is when one of them is 1 and carry is also 1, then carry will be generated. So this is an XOR gate. So if one of them is 1, it will give 1 here. Okay? And you have an inverter here, so it is driving an NMOS, so this will enable this gate. If A and B, one of them is 1, this gate will be enabled. And then in that case, if C in is 0, then obviously C out will be 0. If C in is 1, then output will be 1. Okay, so that is how you generate carry. Now the second condition is if generate, that is if A is 1 and B is 1. So when A is 1, okay, you have this signal coming here, right? And if B is also 1, okay, if A is 1, B is 1, what happens in that condition? It will be 0 out here. So that 0 is being given to the PMOS, and through an inverter it is giving here. So when A is 1, B is 1, in that condition, okay, since this gate is right, it is being PMOS is driven by the propagation, and from an inverter it is being driven the NMOS. So when A and B both are 1, this will be 0 and this gate will be enabled, and this A will come from here to here. So for 1 1 also I get the carry out. So that means this generate part will come from this transistor, and the okay, so the generate path is this, and the propagate path is this. Correct? So that is how the carry will be generated. So this is a full adder circuit, and then obviously you have the propagate and the C in XOR gate to generate the sum also. So this is one, right? Now when I have a ripple carry adder, so I have one full adder, the carry is taken out here. It is being driven and is given as an input to the second full adder. So it is the carry is rippling from one stage to other. So if I have n stages, then the delay will be 2 into n, okay, for this carry to come out. Okay, so this is if you want to so this is carry is 2 gate delays, sum is also 2 gate delays. Okay, so if you see the carry out here, okay, this carry is coming here from one transmission gate is here. This is one, right, one gate, and this is the second gate. Here also you can say A is available here, one transmission gate, second. So on an average you can call this C out is coming after two gate delays. So you have for n stages 2 n gate delays. Okay, so that is what a ripple carry adder. So obviously the delays will be very large if you have a 64-bit adder. So you will have 2 into 64, that is 128 gate delays. Okay, which is obviously not acceptable. So for a small 4-bit, 8-bit adders it is okay, but for where you have large number of bits, then a ripple carry adder will have large delays, which is not acceptable. So we have to look for some other kind of adders. So one adder which is used, which reduces the delay, is known as carry bypass or carry skip adder. Okay, what it does is whenever there is a propagate, like it is generated first, you have four set of P0. Now 4 bits are being added, A0, A0, B0, A1, B1, right? So all the 4. So I guess this should have been P1. Okay, so there is an error out here. It's written P0. It should be P1. So if all the propagates are 1, okay, then you have a multiplexer which will bypass the carry, right? So that is how the carry propagates, right? If this bypass condition is met, okay, bypass is and of all the propagation delays. That means there is a 1 1 here. Out of the 2 bits, you have 1 1. Here also out of the 2 bits there is 1 1. Here also out of the 2 bits there is 1 1. here also out of the 2 bits there is one available. So and hence obviously this carry will straight away will come here. So rather than passing it through this chain, I can bypass it in here like this here, right? So but then the advantage is not evident out here, because suppose there is no propagation here, right? And okay, so that means if both are 1, in that case p is equal to 0, then this mux will not operate. In that case g will generate will come here, right? And from generate the carry will propagate from here to here, right? So the advantage is not seen here, but in the next when we are cascading 2, then the advantages will be seen here. So here I have bit 0 2 3 4 bit, right? And 1 carry bypass adder. This is the next most significant bit. This is the next 4 significant bit. This is the most significant bits. So we'll consider this is not there timing. We are getting the results out here. So in this case what happens is, now the worst case delay situation. So this is the setup time. Setup time is nothing but the time taken to generate G0 and P0, right? So that will be used by the carry, right? Carry propagation. So these are the setup times, okay, which is required. Now once the setup time is given, so this carry has to propagate from here to here, and for the worst case scenario it will bypass this will be the worst case path. It will use these 3 bypass in the worst case path, and then it will because here this bypass is not there, because we are ending the result here, okay. We are talking about a 16 bit, okay. So we are ending the result here. So now it will pass through this all stage, and then lastly this is only carry. So one more some delay will also be required here, right? So the total delay will be given as T setup and MT carry. What is M? And M is the number of stages. In this case there are M is the number of bits out here in each stage, okay. M is, okay, number of bits in each stage, right? So so this is since it is on a 4 bit, so 4 M carry is there, right? And then this bypass, how many bypass will be required? In this case, if it is, you can see there are 3 required. Total number of bits is 16. So 16, and each stage there are 4. So 16 divided by 4 will be 4 minus 1 3. So you see 3 are there. So for a generalized case it will be n minus 1 a T bypass, okay. And then again in the last stage it has to again, because this bypass is not available, this is the last stage, it is an ending stage. So again it has to propagate through and through out here, and then I have a T sum. So 1 bit T sum, after generation of carry you need to generate the sum also of the most significant bit. So this is the total delay. So now you might ask, what is the why is this delay not considered from here to here, okay. So now when will this come into picture is, okay, suppose this is P0 to P3, suppose P4 is not 1, okay, then this will go, right, this bypass will not work, right. But if P0 is not there, this input is not required for carry propagation, because P4 equal to 1 means this carry need not be propagated, okay. That is what it means. That means this chain will be broken here and a new chain will start from here if G1 is 1 here. So it will start from here, a new chain. Again this delay will be, okay, this 1 gate delay, 2 mux and 3 here. So this will be worst case will be this only. This will have if there is a break in propagation, a new chain will start here, okay. So by the time this chain breaks here, so this sum will get generated, this carry will generated here, and here is the, now from the 3rd stage onwards a new stage. But to cater for an so, and hence when we talk about worst case scenario, we take this propagation delay and these mux, okay. So here also similarly, if this mux is not coming in picture, and if this entire stage is being used, in that case this chain will be broken, and if that chain is broken, then a new chain will start from here. So worst case scenario will be this, what is highlighted in gray out here. Okay, is this okay with all of you? Why is this why is that we are not calculating the delay through and through, and what is the advantage of having a carry bypass? Okay, is it okay with all of you? Yeah. Okay, so yeah, tell me, you had something. Okay.
Oh, sir, carry on.
Okay.
That's good.
Okay. So now you have this is a comparison between a ripple carry adder and a bypass adder. So you will find that as the number of bits increase, okay, the bypass adder will have significantly a lesser delay as compared to the ripple carry adder. Okay. Now this circuit is again implemented. Okay, this I want you to study yourself now. So instead of an mux out here, and AND gates have been used, and here an OR gates have been used. Okay, so this is works exactly the same way the bypass or the carry skip. Here we have used, we have not used any, we have directly given here, and we have used a mux in these stages. So this is a slight modification of that. Okay, and this is the delay which you will see in this case. Okay, so this comes as to you as a home assignment. Just try to analyze this particular circuit. Okay, here you will see some buffers have been introduced in between, so neglect those buffers. Okay, so this is not an inverter, it is a buffer which has been put. So just don't worry about that buffer, assume there is no buffer there. So this you can do it as your homework. Okay, so there is another kind of an adder which is carry increment. Okay, this we had not seen in our previous semester. So I have an 8-bit ripple carry adder. This is a 8-bit ripple carry adder, 8-bit and 8-bit. Now suppose I have a 64-bit ripple carry adder. So the total delay will be 64, right? Right? No. This is a 32-bit. So 32-bit into 2 will be 64. 64 gate delays. If you have a normal ripple carry adder, which is cascaded, right? Instead of that, I make this 32-bit into 4 8-bit adders. Okay, and every 8-bit, the least significant bit of each of them, okay, the carry in, okay, I am giving 0 out here. Okay, so all I have given 0. So what is happen, this particular block is not waiting for an carry from here. So this block is not waiting for a carry here, this block is not waiting for a carry which is coming from here. So all 4 of them will start computation at the same time. Okay, and they will give this some outputs at the same time. Now since this is just an 8-bit, 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 okay, 8 into 2 16, so that much delay will be there. Okay, now what I am doing is I am using an increment circuit. Now if this is C1, okay, suppose this carry is 1, I will increment it. If the carry is 0, I will just pass the sum as it is. Okay, similarly this is an C2. Okay, and if I have this sum coming, in case there is a carry, okay, I increment it by 1. If there is no carry, I just pass it as it is. Okay, so this is what I am doing it, right? So separately I have calculated assuming carry to be 0, and then I am incrementing it. Now if I look at this increment circuit, so this is the increment circuit for a 4-bit, okay, 4-bit increment circuit. Now this is the control signal, this carry which is coming here. This C1 is here carry signal which is shown here. Now if you see here, there are 4 XOR gates, and the input is given here, right? So now suppose this is 0 out here, right? So this is it will be 0 out here, and A0, since one input is 0 here, right, and S0 will come as it is. Similarly, this is going to an AND gate, so it will be 0 here. So A1 will get as it is to S1. Similarly, I have a 0 out here, and A2 will get reflected outside as 0 out here through this AND gate. So if this control signal is 0, A0 will come out as it is. So that is what we required here, right? If it is 0, this has to come out as it is. So that will happen out here. But if it is 1 out here, okay, then this is XOR gate. So the first bit it is going to invert it, and then if there is a carry, okay, if there is a carry, again you have an AND gate out here, right? And if this is 1 and this is also 1, right, and this will you will have a 1 out here, okay, so that will invert this, right? So you will find this is how this is going to do an addition of 1 in case, right? For 0 you will get as it is, for 1 you will get +1 output out here. So you can analyze this circuit. Now the thing is out here is, this is for a 4 bit. If you see the worst case path, this is 1 XOR 1 AND 1 XOR 1 OR 1 XOR. So it is 4 gate delays, okay. So, whatever path you take, okay, the worst case is 4 path. So for an 8 bit increment circuit, so the total delay will be 8 gate delays. So this increment will have 8 gate delays, this will have 8 gate delays, this will have 8 gate delays. So if I add 8, 8, 8 out here, so the total gate delays will be 40 for carry increment adder, for a 32 bit carry increment dealer. Whereas if I have just a pure ripple carry adder, the delay will be 64. So obviously this is an improvement over this circuit, okay. So this is one circuit which is known as carry increment adder. Then this is again a widely used circuit which is known as carry look ahead adder. So I have 3 inputs A, B, C, and I have 3 outputs S, G, and P. S is sum. Normally, how is the sum generated? A, B, XOR. Then you get P. P is propagation, and then you take the propagation, and with the carry you do one more XOR, you get sum. Okay, this is what again we learnt in the last semester, right? So A XOR B XOR C is sum, right? So that is what happens here. So A XOR B is available here, again XOR with C. Now this circuits generates an output G as well as an output P, okay. So G means generate. Generate means A and B both are 1. That means you don't have to bother about C. If both A and B are there, straight away it will go into generate and carry. P means propagate. Propagate means only one, either A or B, only one of them is 1. In that case, the carry depends on C. So if carry is 0, the carry in is 0, carry out will be 0. If carry is 1, then carry out also carry in is 1, then the carry out also will be 1. So the carry in needs to be propagated towards carry out. So that is why this is known as propagate. This is known as generate. Now if I try to do how that carry 1 is generated, so this is generate, okay. So that means if both are 1, then this generate will be high and carry will be generated. Now if only one of them is high, then the propagate will be high, right? And then now if you see, you do an AND operation with C0, so P0 C0. So if propagate is high and carry input is 0, then this will be 1, and through an XOR gate you will generate and carry. So this is the expression for carry. So is this 1 bit addition clear to all of you, using sum, using generate and propagate signals? Is it okay with all of you? Yeah, shall we move ahead? Okay. Now if you see, now for 2 bits what do I do, right? Now here if I try to write the carry expression, if A1 and B1, this is the next significant bit, if A1 and B1 is there, then I have to straight away generate carry. So or if one of them is 1 and if there is a carry which is coming from the previous stage, okay. So this is the carry which is coming from the previous stage. And now this carry from our previous example we wrote is a G0 plus P0 C0. So I write G0 plus C0, G0 plus P0 C0. So if I expand this, it will come like now. So this is what carry is generation. if either this is generate or this is propagate and there is a generate coming from here, or if both is propagate and carry is high. So that is can be implemented here. Okay, so this is carry 2 which is generated, this is carry 1 generated. So here straight away there is an advantage. Okay, although the hardware is more, in terms of delay you can straightforward see there is an advantage. What is the advantage? Like this G0 P0 will be generated after 1 gate delay, right? From here 1 gate delay. What about C1? Another 2 gate delays. So at 3 gate delay C1 is available. What about C2? G1 after 1 gate delay. This is one more gate out here. P1 is coming after 1 gate delay. C0 is also coming straight. P0 is after 1 gate delay. So 1 gate delay for this P0 P1, second gate delay, third gate delay. So you will find C1 is also having 3 gate delays, C2 is also having 3 gate delays. Okay, so now if you see here, as I have come from one bit to the second bit, but the carry delay remains 3 only, it is not increased. Now if I expand it to 3 and to 4, right, now if you see this carry 3, okay, same, this expression is expanded, I am going to generate that carry 3 out here. So that carry 3 also is what? From generate, this carry 3 is from generate 2, right, or propagation 2 and generate from the previous stage, or propagation 2, propagation 1 and generate from the previous stage, or it is the all the 3 propagations and carry from here. So carry 3 is also 1 gate, 2 gate and third gate to generate from the top block. Okay, one gate delay is there in the top block. So even carry 3, so for carry 1 2 gate delays, carry 2 2 gate delays, carry 3 also is 3 gate delays. So there is no additional delays as you are moving from one carry to other. Okay, now this particular block I am not going to generate carry 4 in a similar manner. Okay, what I am going to generate is I am going to generate for this entire block and propagate for this entire block. Okay, so this propagate is only AND of all the 4 propagates. Okay, and generate is right, generate is like propagate from the previous and generate from the other previous. So this is what the final carry. If I have to generate, I have to use separately 2 gates. Okay, I am not including this C4 in this block. There is a reason for it. Okay, I'll explain that reason. So this C4 is separate. Okay, now from the generate you will require one more gate out here. Okay, so this is generate and this propagate and C0. So I will generate C4. So the C4 which is coming out after this 4 is going to be from this circuit, which is over and above this what is shown out here, right? Now if I see here for G3 and for G3 it is taking 3 gate delays. For P3 G3 and P3 is this. Okay, this for this block. P3 is only 2 gate delays because there is only one single AND gate out here. This is AND of all the 4 propagation delays. Okay, so this is 2. So again you have to do AND with one more C0, right? So this will become 3 gate delays, this will become 4 gate delays. G is again 3 gate delays plus 1. So I will find that S4 is 4 gate delays, right? S3 again, because this C3, once this C3 is given here, okay, into this block, only then S3 can be computed, right? You have A3 and B3 coming in here, so it will generate P3 and G3 at 1 clock after 1 gate delay, but C3 has to come in. Okay, only then S3 can be generated. And if you go back here, okay, after C in comes one more gate delay. So that is the reason if you go here, this S4 S3 will be generated, C3 is coming after 3 gate delays, and similar, and hence S3 will be generated after one more 4. So the entire operation of this block, okay, carry and sum will be completed after 4 gate delays. Is this okay with all of you? Anybody has got doubt? If you understand this, only then we can see a bigger carry ahead adders. Is it okay with all of you? See, a few points which we have to remember here is, okay, from this block one gate delay is there to generate and propagation. Okay, in this block to generate this carry and propagation, okay, another 2 gate delays are there. Okay, so so 1 gate delay plus 2 gate delays, so total 3 gate delays it will take for this output to come here, right? And to generate these carry 1, carry 2 inside carries, okay, these carries it will take 3 gate delays. Okay, 1 gate delay for this to come and 3 gate delay. For this sum it will take 4 gate delays. Okay, and for the carry for this total is also 4 gate delays. So this much you need to remember to understand what happens in the next stage. Okay, now if I have to make an 8-bit full adder, okay, now I have this one block and I have this one block, so I can give this carry as an input to this block. Okay, now I can't keep expanding this, because if you see here, this AND has already I have started using 4 input AND gates. Okay, when I am using 4 input, and now from our VLSI classes, if you remember, I can't generally if I keep increasing the fan in, the delays will increase, right? And then power also will increase, because you will have to accordingly size the transistors big. So it is a practice to restrict the fan in to 4. So that is why I am not going to expand this further, this block. Okay, by generating G C4, C5, C6. Instead, the same block I have repeated here. Now this carry in will be given here. So the total delay will be 4 delay here, 4 delay here, 8 delay. Okay, so that is how a carry look adder for an 8-bit works like, right? Okay. Now if I have to do it, so obviously this is 8 gate delay for C7 and 8 gate delay for S7. Now if for a 16-bit adder, okay, I am not going to give this input, this carry here, this carry here, this carry here. Instead I am going to use a 2-level carry logic blocks. Okay, so this is the first one is this first blocks which is shown square is nothing but these. Okay, A1, B1, A2, B2. So that CL is not written here. These are all CLS. Okay, so you have A0, B0, A1, B1, A2, B2, and A15 and B15 coming here. So they will give to this block the propagation and the generate signals after 1 inverter delay. Okay, 1 gate delay. So 1 unit. From here to generate P00 for the next block, okay, it will take another 2 gate delays. This we talked about, right? This is another 2 gate delays here. These 2 delays. Okay, because there is 1 gate here, second gate here, right? From the input, if you see here. So this is going to put an additional 2 gate delays out here, right? Now if you see here, so 1 gate delay here, okay, 2 gate delays here, so 3 gate delays. So 3 gate delays are required to give PIGI. PIGI is nothing but input to this particular cell. Okay, and output from this particular cell will be another 2 gate delays. So this will become 5 gate delays. Okay, so is this first 2 delays clear to all of you? Is it okay? How this figure of 3 and 5 has come? Yeah, Rajesh, is it okay?
Yes, Professor.
Yeah, okay. Now, if I talk about C4, right? So this has come here after how many delays? After 3 input delays. Another 2 input delays will be required to generate C2, C1, C2, C3, right? So so that not C1 from here, which is actually C4. Okay, this is C2, which is nothing but C8, and this is 12. So 1 gate delay from here to here, 2 gate delays here propagation. Within this block, another 2 gate. This block is nothing. It is shown big, but it is exactly the same block, right? It is the same block. same block, it is just shown big out here. Okay, this is also 2 gate delays, so this will take additional 2 gate delays. So this will be C4, C8 and C12 will be additional 2 gate delays. So there will be 5 gate delays in producing. Okay, now this P and G has come after 5 gate delays. Okay, so C16 will be one more gate delay, that we saw, right? In this block we saw, right? After generating G and P, you require one more gate to generate the carry output of this particular block. So similarly, if I consider this as a whole big block, to generate C16, one more gate delay. So 6 delays for C16. Okay, that is C16, right? So that is done. Now this is generated at 7 gate delay. Okay, so this one five gate delays, right? Now that is going as an input out here, input to this stage. Okay, now it will take 2 gate delays to generate C15, carry 15 for this stage, because here also once this input is stable, it will, there are 2 gate delays here. So 5 plus 2 7. Okay, so C15 will get generated at 7 gate delays, and for this to generate sum, it will require one more gate delay, because sum is again here. If I go back here, once this carry is available, for sum you require one more gate. Okay, so that gate will be required here for the 16th bit once this carry is available. So one more gate delay, so 8 gate delays. So this 16 bit full adder, the total delay will be 8. Is it okay? Is this computation clear to all of you? Yeah, Krishna, Ramya, Pradeep, anybody? Is it okay with all of you?
Yes, clear.
Okay. So if I talk about an k bit look adder, okay, so this will be 4 log 4. Okay, this means you need to round it off, okay, to the multiples of 4. Okay, so that is why the symbol is given like this. So for a 4 bit it is 4, for a 8 bit it will be 8. Okay, that we have seen here. Where was the 8 bit? For 8 bit it was 8, right? So it is not written in the table for 8 bit. For 16 bit also it will be 8, because for 16 bit also 2 level will be okay, right? For 16 bit also 2 level is okay, and hence it is an 8. For 32 you will require 3 levels, right? So for 3 levels it will be 12, right? And for 64 also it will require 3 levels only, because when I talk about 3 levels, okay, in the third level I can take a total of 4 sets of inputs. From these 216 I will get only 2 sets of inputs. So from 32 to 64 it doesn't increase the number of levels, right? So that is why it is 12. You understood? You require one more CLL, right? So every 4 set of inputs, one CLL can such if you have 4 of them, then below you can have on the higher level you can have one more. So that is the reason for 64 also it is 12. Okay, so as compared to the ripple carry adder, if you see here, now if you see how much it is, almost 10 times faster than a ripple carry adder. So modern day processors which are operating at 64, so for a carry look adder it can work 10 times faster than a ripple carry adder. So these kind of adders are very much in use in the industry. Okay, so the only penalty out here is increased hardware, okay, as compared to the ripple carry adder. Okay, so that is the penalty which you pay out here. Now if you see here, when we were talking about the gate delays out here, I said okay, this is 1 gate delay, this is 2 gate delays. I am computing like that, 1 gate delay. But you might want to tell, sir, this AND is actually NAND followed by an inverter, this OR is actually a NOR followed by an inverter, because you can't in CMOS you can't make an OR gate. So actually this is 2 gate delays, and so hence from here to here it should be 4 gate delays. But that is not actually the case. The thing is these two together can be implemented by this circuit. Okay, if you see here, if G is 0, this will be pulled to 0. G is 1, G0 is 1, this will be pulled to 0. Otherwise, if P0 is 1 and C0 is also 1, this will be pulled to 0. So, you will get C0 bar out here, and then you put one more inverter. So, if you see here, these two gates have been combined by this circuit out here, okay, and then you put one more inverter. So, these two together will actually bring in only 2 gate delays, okay. So, that is the advantage. So, that is the reason why we didn't stress upon that point that this is an OR, this is an AND. We just considered this as AND, because in combination these two together will introduce 2 gate delays only, right. The same is the case for this also out here, 2 AND 1 OR, that can be implemented like this, and this also can be implemented like this, right. G2 or G1 into P2 or G0 into P1 P2 or Cn into P0 P1 P2, and this the dual is made from PMOS out here. So, you will get here, okay. So, you can size these transistors for a unit delay, and then you will this is inverted, right, it is going to pull down it. So, you will have to use one more inverter to generate. So, all of these transistors, okay, they can be implemented like this, okay. This is for the last C03. It can be implemented this way also, instead of this you have so many stacked. So, this also is one option of implementing it. Here if you see here, if G3 is high, okay, this transistor will be on and this node will be pulled to 0, and then you use one more inverter to get the correct carry. If G3 is not on, then if P3 is on, right, and then so this will be enabled, and then if G2 is on, okay, so P3 G2, okay, that will also pull it down to 0. Otherwise, P3 P2 and G1, okay, that will also pull it down to ground, or P0 P1 P2, right, P1 P2 P3 and G0, okay. So, that will also pull it to 0, okay, or just P1 and then C1, okay, that is. So, this way also you can implement it, okay. So, this is again a Manchester carry chain. This is for dynamic logic. So, whenever we are implementing dynamic logic, you will see the number of transistors is further reduced drastically. Now, when the clock is actually low, all these nodes will be pre-charged to 1, and you have carry going 0, because this will be pre-charged. Now, if when the clock is going high, the top all the PMOS will be out of action, and all the NMOS here in the bottom row will come into play, right. If they are 1 and G4 is 1, right, it will be straight away pulled to 0. So, generate 4, okay, this. Otherwise, if G4 is not there and if P4 is there, then it will look behind, and again G3 if it is 1, then this will get discharged in this path. So, either it will get discharged through G4 or it will get through from G3 into P4, okay. Otherwise, if even G3 is off and I have a P3 P4, then G2, okay. So, there is a path available here, right. The next path which will be available out here will be G1 into P2 P3 P4, right, or G0 into P1 P2 P3 P4, or carry in is there and then all the propagation is high. In that case also this will get grounded, and then you have an inverter which will get the carry. So, this is this simplifies the total circuit and the total number of transistors. The only thing is it is a dynamic logic, so it needs to be pre-charged, and it requires a clock for its operation, okay. So, this is known as Manchester chain carry, right. Then another circuit which again is used in many places is known as linear carry select order, select adder, okay. So, what exactly is being done out here is, so you have 3 bits out, 4 bits out here, 4 bits. You have a 16 bit, you have made it into 4 bit, okay, carry blocks, and then you are assuming the input carry here to be 0, and you are assuming the input carry to be 1, and parallelly you are doing computation, okay. So from 0 this input is not coming to this block, okay, this carry is coming directly to the mux. The output of this is also directly coming to the mux, okay. I guess this arrow should not have been there, right, okay. So this is not feeding this, okay. So these are two blocks which are parallel to each other, right. In fact, this, if this is not there also, there is no issue, I guess, okay. So this carry is going to come here, this is, so this is taking 1 as an input, okay. No, this arrow is coming from the top, from the setup, okay. It is not coming from this block, it is coming from the setup, okay. So that so from the setup I am giving simultaneously input to carry this block and this block. For this block I am assuming the input to carry to be in to be 0, and for this block I am assuming the carry input to be 1. So parallelly I do the computation, and once I do the computation, it is available to a mux, and then depending on the actual carry which is there, okay, I will select either if it is 0 I will select this, if it is 1 I will select the bottom. So now what happens is, now this particular block is not waiting for an carry to come from here, it is calculating the carry, assuming it to be 0 and assuming it to be 1. So this is also available. So parallelly all these 4 computation will complete, and it will be available to the mux. Now the only task is to select the appropriate mux, that's all, because parallelly all these verticals are doing the calculations without waiting from any input from the preceding stage. So all the parallel blocks are doing parallel computations without waiting any for any input from the preceding states, okay. So now on this input is available here, depending on the mux the correct carry will be selected. So if I talk about the worst case delay, it will be 1 setup, and this is carry, okay. Now how many bits are there? If total number of bits are n, and if total number of stages is m, so m is total number of stages, okay. M is the total number of stages in this particular case, okay. M is the total number of stages, okay. So n divided by m is the total number of bits per stage. So that into t carry will be the delay in this one particular block. So that delay, okay. Now both these delays need not be computed, because they will do parallel computation, one of them needs to be selected. And then how many multiplexers are required? 1, 2, 3, 4. That is an m multiplexers, because m stages are there, so m multiplexers are required. And then finally the sum requires to be generated in the last MSB. So 1 t sum. So this is the total delay which will be encountered in a linear carry select, okay. It is called linear because if you see the total 16 bits, 4 4 4 4 equal number you are dividing it, okay. So this is not a very efficient way of doing it. So we have an alternate option available with us, which is known as square root select adder, in which here we are having 2 bits, here we are having 3 bits, here we are having 4 bits, here we are having 5 bits. So the advantage out here is, like this will do 2 bits carry generation, and then there is one multiplexer delay, okay. So by that time this output of the multiplexer is available. Here I am adding doing a carry operation for 3 bits, okay. So that wait time of one multiplexer is I am utilizing it to generate one more bit of carry. Now here if you see here, this is 3 plus one more multiplexer delay. So here I am using 4 bits. So 5, 6, 7, 8, 4 bits. Similarly here another additional one more bit is 6 bits, okay. So as I keep moving like here, since there is additional multiplexer delays which are being introduced, okay. So just to take advantage of that additional delay, I am increasing the number of bits progressively by 1 when I move from one stage to other. So that is known as carry root select adder, okay, square root carry select adder, okay. Now if I talk about the total delay, it will be a t setup plus m t carry. Here m is not total number of stages, okay. M indicates the minimum number of bits in the total number of bits in the first stage. In this case 0 and 1, so m is equal to 2, okay. So this is 2, and then mux. Total number of stages is square root of 2n. Why did this total number of stages come as square root of 2n? We will see it in the next slide. Okay, so those many t mux and then one t sum. And since the total number of stages, total number of stages, vertical stages is square root of 2n, this name comes from there, square root. Okay, now why this square root of 2n? That we will see here. So suppose the first stage has got m bits, the next stage will have m plus 1, the next stage will have m plus 2, and total number of stages is p. So the p stage, the pth stage will have m plus p minus 1. Okay, so this is 0, this is p, so this is, that is the total number of bits. Now this is a series, right? This is series. If you add that series, you get if you use this formula, you get mp plus p into p minus 1. And if you multiply this, now if you consider m, the number of bits in the first stage, like for example here we took only 2 bits. So if m is equal to 2 and a total number of bits is n, so m is much lesser than n, right? So this becomes negligible. So you can neglect this term. So this become n is approximately p square by 2. Okay, so p is equal to square root of 2n. That means the number of vertical stages, okay, which is p, which is square root of 2n. Okay, so that is the reason why this name comes from square root. So obviously this is better. Now this is a graph which shows this is a ripple carry delay, this is linear carry select as you keep increasing n, and the bottom dark thick black line is for square root select. Okay, is it okay till here? All of you, anybody has got any doubts? Is it okay? Yes, shall we move forward? Okay. So we have another kind of adder which is known as carry save adder. Okay. So what is carry save adder? Now suppose I am adding these 3 bits. Okay. Now I am just not bothered about the carry, I am just writing the sum here. Okay, 1 plus 1 plus 1, sum is 1, 0 plus 0 plus 1, sum is 1, 0 plus 0 plus 0 is 0, 1 plus 1 plus 1, sum is 1. Okay, I am just doing a full adder operation, I am writing the sum here. I am writing a carry by shifting it towards the left. Okay, 1 plus 1 plus 1 will generate a carry, it is carry. 0 plus 0 plus 0, 0 plus 0 plus 1 will not generate a carry, so it is 0. 0 0 0 is sum is 0, carry is 0, so it is written here. 1 1 1 is sum is 1, carry 1 is there. So this carry is a shifted 1 here. Now I am generating sum and I am generating it carry and then I am adding it. So I get 1, 1 plus 1 is 0, 1 goes here, this 1 plus 1 1. So I am still getting the same answer. Okay. Now hardware wise, so if instead of carry forwarding this ripple like this, okay, I have one set of 4-bit adder here. Okay, again I have one ripple carry adder here, right? If I take the carry out here to this, if I put the sum here, if I put the carry here, sum here, this carry, okay, this sum is coming here, this sum is coming directly here, this sum, this carry is going to the sum of the next. So this is one more ripple carry adder, right? So this carry is being added with this sum, this carry is being added. So this is what this is implemented here. Now finally this is a 0 for this last bit. So this is a 0 because this is only the carry which is there. So I am putting a 0 out here. Now if you see here, if I have a normal ripple carry adder, then the delay will be 2 into n, right? So 4 into 2 8. Whereas here if you see here, this is just one full adder delay. All these outputs will be available after 2 gate delays, and this is a ripple carry adder, right? So it will be just 4 into 2 8 plus another 2, only 10. Otherwise this would have been 16, right? 8 into 2 16. So you find and this is much better. So this is what again a little bit of hardware extra, one full set of adder is there, but then it is much faster than the previous option available. So this is known as carry save adder. Okay, this is again this we didn't learn it in the last semester, right? Serial adder, which we did in the last semester. So in serial adder, generally you have this is for high frequency operations, where if the clock frequency is very high, then these kind of circuits will work very fine. So if you see here, for a 4-bit, I have a 5-bit register. So initially the data which needs to be put into the accumulator is put here, right? Okay, this is put here. This data is put out here, right? So this sum will be available here, carry will be allowed. This register also needs to be initialized with 0, and these two bits of this 5-bit register also needs to be initialized to 0. So there will be 0 here, there will be 0 here, there will be 0 here. So during the first clock, what it will do, it will add x0 y0. This sum is available here, that will be pushed here, right? And I have this carry here, okay, that will be pushed into the D register. So in the first clock, this sum will come here, right? And this x1 will move here, y1 will move here, y0 will be pushed here in this particular case. Sum will come here. And now in the second clock, now this will do the addition now here. What is this addition? The new data are available, x1 and y1 will be available here, and the carry from the previous addition is available here, right? So it will do that, and then a new sum will be generated, that will be pushed here. So at the end of 5 clocks, I will have the sum available in the top register. In the bottom register, at the end of 5 clocks, I will have the including the carry will come here, okay. 4 clocks, this data will come here, and then this, when this 0 comes here, okay, this 0 also, you have initialized both these registers with 0. So this will come here 0, end of the 4 clock, 0 0 will be available here, but the carry from the 4th bit addition will be available here. So one more clock, that will push that final carry which was available here by adding x3 and y3, okay, here it will become 0 0, that will come here. So 4-bit additions and will give me a 5-bit answer. So that 5-bit answer will be available in the accumulator, and in the addendum register, whatever was the previous data, okay, that will be again pushed in back here, okay. So that will be available here, okay. So this is how it works. So what would be the advantage and disadvantage? Can anybody guess? Yes, yeah, Kulkarni, Karishma, anybody? What is the advantage?
Minimal hardware.
Pardon?
Minimal hardware.
Yeah, very minimal hardware. So even for 64-bit adder, I will require one 64 register and one 64-bit register here, and just 1-bit adder. Okay, this is 1-bit adder, irrespective of the number of bits which is there. This is just one bit adder and one flip flop. So minimum hardware is required. Only disadvantage is it will take those many clock cycles for it to. See, if it is 64, then 65 clock cycles will be required for computation of this data. Okay, so that is the only disadvantage. But then when we are working in megahertz range and all, then obviously this is very the delay out here will be comparable to the delays of these circuits. Okay, but when we are talking about in gigahertz range, this clock is very high, right? So you can. So now if you see here, this is what is the element which decides the clock frequency in this particular circuit? What puts a restriction on the clock? How much delay you have to cater?
The adder.
Yeah, one bit adder, that's all.
Yes.
Correct? Just 1-bit adder. So only that much delay you need to cater. Whereas in these circuits, if you see here, this is the kind of delays, right? So your clock frequency will be has to cater for this much delays for whatever circuit we have combinational circuit we have discussed till now, right? You have to. So this is for for fast clock operation, right? So area wise. So this is one of an a very good circuit which can be implemented at high frequencies. Okay. Now before talking about a few more adders, okay, let's try and understand what a dot operator is. Okay, what a dot operator is, I have a G0 P0, okay, generate from G0 and propagate from P0. Again I have generate from G1 and I have generate from P1, and I do a dot operation. Okay, as I am doing then, and what an if I do a dot operation, it will generate G01 and G01 and P01. Okay, so and G01 is given by G1 plus P1 G0. That means it is a combined generation of these two. So G1 into P1 G0, and P01 is just AND of these two. So this is how what a generate a dot operator does. So hardware wise, what is a dot operator? It will have one AND gate, right? For this, it will have one OR gate and one AND gate and one more AND gate. So this dot operator is actually, right, it has got two sets of inputs. G1 P1 G0 P0. Okay, and this is an hardware which is known as a dot operator. Okay, and the output is G and P, right? And how is this G generated? By this G will be generated by an OR gate, and then you have an AND gate P1 and G0. Okay, and this will come as a this thing. And how is this P generated? P is just an AND operation of P0 and P1, right? So this is a dot operator. So this is the hardware inside that dot operator. Okay, so I do G0 P1. So so this is what I get. Okay, and if I have to generate a carry, I can use this expression again, right? So if I do a dot operation of already I have generated 1 3 and P3 through some operations, and G2 and G5, and if I do a dot operation, I will get G15 and P15. Is this clear to all of you? Only if this is clear, rest of the things will be understood. Is this clear to all of you?
Yes, Professor.
Yeah. Okay. So okay. Now if this is what a dot inside the dot operator, it is just these three gates are there. Okay, that's all. So now if you see here, now I am generating first gate. I am doing an 4-bit addition. Okay, so I am talking about what a parallel prefix adder is. So this is a Kogge adder, how it looks like. So in the first stage, I am going to generate from A0 B0. I am going to generate G0 P0. For from A1 B1, I am going to generate G1 P1. From A2 B2, I am going to generate G2 P2, and from A3 B3, I am going to generate G3 P3. So one gate delay. Okay. Now this is a dot operator. Okay. This dot operator, I am giving these two inputs here. Okay. Actually, there are two inputs to this dot operator. A dot operator requires, right, G1 P1, G0 P2. So here it is. So these two, both G0 P0 is going, G1 P1 is coming here. So I will get 0 1 out here, because this is going to combine these two, right? Again I am going to use combine these two. So I am going to get 1 2 here. I am going to this is again a dot operator. So this is going to generate 2 3, right? But with G0 P0, I can generate C0. But for C1, to generate C1, I have G1 P1. I require G0 P0 also, right? So this is this is an 0 and 1, both are available here. So C1 I can generate. C2, this is giving just 1 2, okay. This is giving 0 1. 1 2 is not adequate to generate an C2. So I am taking this also, and again I am using the second level of an operator here. Okay, this is combining the output from here and this output to give 0 3, which I will use to generate an C2. Similarly, this, okay, this is this is just giving 2 3, okay, and this is giving 0 1. So if I combine this 2 3 and 0 1, I will get 0 3. So this 0 3 output is required to generate carry. So obviously there are two stages of here. So 2 into 2, 4 gate delays, okay. That is actually, it is log 2 4. This 4 is the total number of bits, okay. So 2 into log 4, okay. So 2 into 2, 4 gate delays, 2 stages are there, okay, 2 stages are there, number of bits is 4. So total gate delay will be 4 here. Again from G0 and P0, okay, to generate an carry, it will take 2 gate delays, right, that we saw early itself, right. From generate and carry, if you go to the very first few slides, okay, here from generate and carry, it's going to take 2 gate delays. So that is what it is taking out here, 2 gate delays to generate and 1 more gate delay to generate the sum. So if you see total gate delays for an 8-bit adder is 1 gate delay plus 2 gate delay 3, 3 plus 2 5 plus 1 6, total 6 gate delays. But obviously this much of hardware will be required. Is this thing clear to all of you? How an parallel prefix adder works? Okay, all these this is actually hardware which combines this is a hardware consisting of 3 gates which combines G0 P0 G1 P1, okay, and this is an hardware which combines G1 P1 and G2 P2, right. But for carry 2 I require everything, I require the entire thing together. So I require one more dot operator out here, okay. Is it okay with all of you?
Yes.
Okay.
And
so
how much will it take if we implement entire 8-bit adder using carry look ahead instead of
this is 8-bit, right? So total gate
yes,
is
yes.
1 gate delay plus 6 gate delays. It is 7.
Yeah, this is
plus 2
using
9
the
plus 10.
Coxstone method.
Yes.
Yeah. I'm talking about conventional carry look ahead method.
Carry look ahead adder for 8 we took 8 only. For
yes, yes.
8-bit also it was 8.
Okay.
Right? Okay. So this is now now if you see here this is for this we did right now, right? Okay. Now this is for another. So if you increase this number of from 8 to 16, only 2 gates will be added. 2 more gate delays will be added, correct. It will amount to one more set of one more row. So if you see here, if you keep increasing, because this is the formula which is used, so here it is shown here. So if you keep increasing, so so it will not, it is in logarithmic scale only, it will increase. So it is not like a ripple carry adder will keep multiplying. So it will increase. So as you keep increasing the number of bits, okay, so the delays will not increase to that particular extent, okay. But the problem out here is increase in hardware, okay. So there is lot of hardware. So there is a modification to this also. Now this is the thing which we learned, right? Now if you consider,
can you please go to a previous slide?
Yes.
One more. So the total delay of that means maximum delay will be the addition of all these bits. 1
Yes,
gate delay
yes.
plus 6 plus 2 plus 1. Okay.
Correct. Right.
So
Okay.
correct, correct.
So now if you keep increasing the this layout and thing will increase, it becomes very complex. Okay, so now I have redrawn the first circuit out here, and I am just concentrating on the 0 to 7. Okay, for 0 to 7 what all do I require, right? I require 0 to 1 here, this is become 0 to 3 here. Okay, and I am requiring this 0 to 2 to 3 is required here, because that is generating 2 to 3, and this 4 to 5 is required here, 6 to 7 is required here, that is become 4 to 7, and between 0 to 3 I am getting 4 to 7. So now this all those which are not required for generating C1 has been removed here. Okay, now so only 1 2 3 3 6 7 is only required, correct? All those which are not required has been removed here. So after removing, this is how it looks like. Now if you see here in this here, this is okay, right? This is also okay, this is also okay, but here I don't have 0 to 2, correct? I don't have a 0 to 2. So let me introduce 0 to 2. So I put one more adder out here. Okay, this is available, this is available, right? So I take these two inputs and I generate 2. So this was available already, right? And 0 to 3 is available here. So that is available here. I don't do anything. Now this was not available for me here, right? This was not available. 0 to 4 is not available. So now 0 to 3 is available here. 4 to 5 is available here. So I insert one more dot and I get 0 to 4. Okay, so now 0 to 5 is also not available here. 4 to 5 is available here. Now 0 to 4 is available here. So now 0 to 3 is available here, 0 to 4 is available here. So I can use that and generate 0 to 5. Similarly 0 to 5 I can use it to generate 0 to 6 here. So this way now I have generated all the required ones. Now compared to the earlier ones, you see I have removed all the redundant ones. Okay, here if you see it was 1 2 3 4 5 6 7 8 9 10 11 12 13 14 15 16 17 odd were there. Here I have 1 2 3 4 5 6 7 8 9 10 11. Okay, so there is a first Stone proposed this diagram. Okay, and then he implemented it. Then Brent later on realized that this can further be improved, so he came up with an improvement of this from here to here. He said, okay, we can further optimize it like this. So he has removed a few of the gates. Okay, so it may not, you can see a little bit of improvement here, but when you talk about in a 64-bit or in 16-bit, you will find the improvement is much higher. Only thing is the algorithm is slightly complex out here for an 16-bit. This is a simple algorithm. Every row, whatever is available, you keep doing it. So whereas here the algorithm is slightly difficult, but then the total number of transistors which are required, that is much lesser. Okay, so these kind of adders are also used these days. So whenever there is a requirement of combinational logic, okay, so these are the ones which is the although for discrete components, discrete ICs, right, it is mostly carry look ahead adders. Okay, these kind of adders for the discrete circuits, whether it is a TTL adders and also many ICs you find these days, they are all using combinational logic only, right? For VLSI circuits, high frequency serial adder is used. So this is a very important circuit for you all. Okay, you should know how this functions. Okay, this is there. Again, in the VLSI domain, okay, in the VLSI domain, okay, if there is a discrete if a combinational circuit is to be implemented, then this is the adder which is presently being used. Is it okay? For discrete carry look ahead, for VLSI combinational, this is the one, and for VLSI high frequency applications, serial adders. Okay, So these are the kind of adders which are used in the modern day circuits. Okay, so I think we'll stop it here for today. Thanks a lot.